Hello everyone, welcome to my talk. My name is Wang. I'm a member of AMD APIC Linux kernel enablement group. I'm working on secure virtualization. Today I'm going to talk about secure interrupt delivery for SEV-SNP guest. First, I will give an introduction about what the problem is, and then what the solutions are. Then I will talk about one solution, alternating injection. Basically, what the alternating injection is and what we need to be done there. So, why is a secure interrupt delivery needed? The answer is the hypervisor is untrusted, but it's in control of interrupt injected. The malicious hypervisor can decide when and where to inject the interrupt. Sorry. Well, if the guest is not ready for handle the interrupt, its execution could be compromised. There are already some attack examples. Take one example. The malicious hypervisor can inject the interrupt 29 at any point in time. It can trigger the PON-VC handler and control the value in the exit reason register. These are very powerful primitives for the attack. So it can break the confidentiality and the integrity of the guest. We can see the problem is pretty severe. So to prevent the attack from happening, we need a more restricted interface between virtual machine and the hypervisor regarding the interrupts. So the virtual machine can selectively accept or drop the interrupt. In other words, the guest is in the control of the interrupt delivery. Therefore, it can protect themselves. So between the interface of untrusted hypervisor and the SNP guest, there are three protect solutions: restrict injection, alternate injection, and secure APIC. Those are all hardware support features the SNP guest can use. Restrict injection disable the interface interrupt queuing and the injection interface, while the alternate injection it still keeps the standard virtual interrupt queuing and the interface, but it's controlled by the guest itself. The secure APIC is advanced virtual interrupt controller. It is a hardware acceleration. Among those three protection solutions, restrict injection and alternate injection already supported in the current hardware. The secure APIC will come in a future part. Before we move forward, let's take a look at the difference between restrict injection and alternate injection. So restrict injection have a better performance than alternate injection. The reason is there's no virtual machine privilege level transition. However, it's not preferred for a Linux guest. It's facing obstacle upstreaming. The reason is x86 exception handling. More specifically, the nested exception detection is problematic. So we have a concern about the nested PON-HV detection is not reliable. So we switch to alternate injection. In alternate injection, the restrict injection is used to inject into a secure VM service module. So it requires VMPR transition. However, it doesn't have the concern related to the restriction injection has above. The reason is SVSM is simpler. It can handle nested exception properly. So we focus on alternative injection. Next, I'm going to talk about what alternative injection is and what is need to be done there. Let's take an overview about alternative injection. So the hypervisor gonna use the restriction injection to inject the interrupt into the SVSM. By using restriction injection, we can protect the SVSM from the malicious interrupt. Therefore, leave the guest OS safe. SVSM is running at VMPR ZISO. It is a trusted entity. So the SVSM will do the, sorry about that. The SVSM will use alternate injection to present the interrupt to the lower VMPRs by writing to their VMSA. To support this scheme, the following is what we need to do. So first, we need KVM support for restriction injection into the VMPR ZISO only guest. In the traditional injections, the general interrupt, NMI, and the machine check, they will be injected into the guest OS directly. With the restrict injection, of course, first we need to enable restrict injection, which include hardware support and the guest request. We are going to disable all of the all of the hypervisor-based interrupt queue and the interrupt interface. Instead, we will have a new exception vector, PON-HV. All of the general interrupt, NMI, and machine check will only be able to inject with the PON-HV. And the interrupt have to go through a trusted filter. It's controlled by the virtual machine itself. Besides that, we also need a KVM support for GCB restriction injection non-automatic exit events. There are PON-HV doorbell page, which will register a doorbell page with PON-HV for communication between hypervisor and the guest. There's also a PON-HV API. If you needed to send the API around those vCPUs. Also, there is a new required feature for restrict injection timer. If you request timer support from the hypervisor when the restrict injection is enabled. Next, let's talk about what we need to be done for KVM to support the alternate injection. Let's take a look at the alternate injection flow, then see what we need to be done there. So when we need to inject interrupt for VMPR1, of course, with the alternate injection, of course, we need enable the alternate injection in hypervisor, which also include hardware support and the guest request. Also, the KVM need to support to inject the interrupt to the different VMPR levels. It inject interrupt into the SVSM with the PON-HV first. Then the SVSM will do alternate injection by going through SVSM APIC emulation. Then write the interrupt to the AMSA of the VMPR1. Afterwards, request to switch back to VMPR1. So the hypervisor gonna run VMPR1 and start to handle the interrupt. Here comes a kind of a key questions point, like why SVSM can do the alternate injection instead of a hypervisor. The reason is SVSM is running at WaveMPR 1, and it can write the guest private memory, which is a VMSA. So that's the main reason about that. Besides that, there are proposed changes to the GCCB to support the alternate injection. There are two parts. One is the changes to GCB NAE events. One, we need to configure injection notification vector, which will be used by the hypervisor to notify the SVSM about interrupt injection processing. Disable alternate injection. It requests the hypervisor to disable alternate injection for a specific VMPR when this VMPR doesn't support alternate injection. PowerHV timer. We need to extend the PowerHV timer for the timer interrupt for a lower VMPR. There's also a specific EOI for a level sensitive interrupt. It will avoid the risk condition when the hypervisor is processing a new level sensitive interrupt request, while the SVSM is still working on complete EOI for a lower priority sensitive interrupt. And we also need to have extended interrupt information for multi-VMPRs. Now, let's take a look at what needs to be done for the SVSM itself. So the hypervisor, as we talked, it needs to use the restrict injection to inject interrupt into the SVSM. So the SVSM first, it needs to enable restrict injection. Also, it has to be able to handle the PowerHV exception. Then we also need the APIC emulation, which we'll use to present the interrupt to the lower VMPRs. Also, the APIC emulation will protect the guest state in the guest itself from leaking to the hypervisor. Besides that, we also need the SVSM APIC protocol. It's used for the lower VMPRs to configure its APIC state through the SVSM. Before we move to the next slides, I want to talk about traditional APIC protocol. So we have this in mind, then we move to the next. So traditional APIC protocol are using KVM APIC emulation. When the guest needs to modify its local APIC register, it will send a request to the hypervisor. The hypervisor gonna use the KVM APIC emulation to handle this request. Obviously, we can see all of the sensitive information will be leaked to the hypervisor. That's why I want to have this in mind, so we can move to the next. So next is what we need to do for the Linux guest to support alternate injection. So let's take a look at SVSM APIC protocol flow. When the guest need SVSM APIC request, it will prepare the SVSM APIC request. It involved written to the SVSM calling area. After it's done, it's gonna request to switch to the VMPR ZISO, which is the SVSM. The SVSM gonna process this SVSM APIC request, then switch back to VMPR1. The VMPR1 gonna process SVSM APIC result. From what we can see, obviously, the hypervisor is only responsible for the VMPR switch. So there's no sensitive information will be leaked to the hypervisor. So simply, what we need to do for the guest is we just need to enable the alternate injection for the guest and inlet the guest for the SVSM APIC protocol. So for alternating injection for the guest, there are two parts. Firmware and the guest OS have a separate enablement. Worth to note, those are only the changes that need to be done in the guest. So let's summarize what we are right now. So for KVM support for restrict injection into the VMPR ZISO only guest, we have sent the patches upstream for review, and the patches support for most of the GHCB requirements. The PON-HV API and non-EUI required is still under development now. As to KVM support for alternate injection, the SVSM hypervisor support is multiple VMPR support is still under development. There's the talk about that yesterday from my colleague Tom Lantaki, and also Jörg and Rory from SUSE. They have a talk from that too. I mean, if you are interested, it's worth your time to watch their recordings. So after that, then we need to work with the multi-VMPR support to track a separate site interrupt source for each VMPR. Then for Linux guest support for alternate injection, it's under development right now. The last is the SVSM support, restrict injection for VMPR ZISO, APIC emulation, and SVSM APIC protocol. Most of them code are already pushed in the Coconut SSM by John Line from Microsoft. The restrict injection for lower VMPRs, it will be done in the future. These are some reference link if you are interested. Okay. Thank you. I'm open for questions.
So I don't fully understand the, thanks a lot, amazing presentation so far.
Thank you.
I don't understand the problems with restricted injections. I heard that the upstream conversations went south and everything was bad, but I don't understand the technical reason why an SVSM is able to serve an HV in a re-entrant way, but Linux can't, and whether alternate injection actually solves a completely separate problem from the nesting, because it also pulls APIC emulation into the guest, which then has completely different additional side effects. So what exactly is the real problem with restricted injection?
Are you talking about a restriction, the problem in Linux guest directly?
Yes.
So I think it's the legacy problem in the x86. I think it's about the stack transition. So they have the problem with detect the nested exceptions. But in SVSM, it's much simpler.
Why?
I mean, it doesn't have the legacy problem because I think Europe probably can help answer that question.
An HV, oh, thank you, Jörg.
So the problem is the HV exception, which can come at any time. You cannot block it. It can even come while the HV handler is running. So the HV handler must be IST, and when you get another HV while the IST handler is running on the IST stack, you're basically screwed, right? So, and the Linux entry code is already not easy, let's say. It's actually pretty complicated. So, and the upstream maintainers were not keen to complicate it anymore with another NMI-like exception type like HV.
So the HV handler overrides the stack pointer, right? if it's a normal interrupt.
So Coconut does not have to use the IST for a bunch of the vectors that Linux does. Linux uses the IST for anything that can happen in the syscall gap, right? So NMI, machine check, DB, so on. And because those can nest, it makes the detection of whether you already had an HV harder. I think we had some patches for that. I think, was it Peter Z who didn't like them? But Coconut doesn't have all those other things because it doesn't have a syscall gap. So it doesn't have to use the IST. I mean, it doesn't use syscall at all, right? So it doesn't have to use the IST for, I think, anything other than double fault, right?
Just based on the experience, the discussion which we had with Peter Z, we try to convince the little bit handling of nested exceptions, which already was there with NMI and VC existing similar for HV, but he said that if you add more things, it will be harder to later find out if it clobbers the syscall gap later. So it's not a one solution. So the solution was the Fred later. So that's what he suggested. But I think secure AVIC doesn't. The
question is, will secure AVIC solve it?
Yeah, it will solve because I think that it doesn't give the HV point HV. It does whatever handling is done with VC little bit, and there's no IST nested IST exceptions for secure AVIC.
Okay, so once we have a secure AVIC, there's no need for for alternate injection. We can just simply pass in a secure AVIC and everything is good.
Yeah.
Well, that's almost true, but unenlightened guests that want interrupt protections would have to run with alternate because that's the only way you can fully emulate an APIC.
I think we had the conversation multiple times over this event. I don't think that confidential computing and unenlightened guests are a sensible combination. So we can just assume that with a secure AVIC world, we will have the ability to not have the alternate. It's just a lot of overhead, right? Like jumping back and forth between VMPLs, all of that is software switching, is just slow and tedious. And it also pulls in another emulator into my TCB, which I really don't want to have, yada, 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 right?
I hear you, but that there's more opinions to that. Sorry.
You might not like the more opinions. My question was going to be the same. From an upstream perspective, like ignoring CSPs or downstream people that want to take on the tech debt of this, from an upstream perspective, why shouldn't our stance be give us secure AVIC?
Well, we have 2 generations of hardware that are out currently that don't support it.
Which is a good argument for the CSPs and the downstream people, but from an upstream perspective, what's there that makes it worth supporting for 2 generations?
Lots of people who have hardware that they would like to use.
So I have a question that's more also on the Coconut HV thing. What makes Coconut not have a syscall gap, since Coconut also has user space?
Syscall just uses Coconut just uses int 80 as the syscall entry point. It does not use syscall right now, and we also don't use it for swap.js because we don't use JS in the kernel. For pure CPU, we have pure CPU page tables where the pure CPU area is actually mapped at a fixed position, so we don't need JS as well. So that's why we don't need IST for anything but double fault. So yeah. It's not performance. The question was whether it's for performance reasons. No, it's actually for keeping things simple. So yeah. Right.
Thank you.